So hi everyone, I'm John DeGoes, and I am very happy to be here down in Denver. Do we have any Boulder functional programmers? No, I'm kind of disappointed. We were supposed to have a few Boulder functional programmers who came down for this, but oh well. So today I have, I want to first thank Joel and Heath for inviting me here. I mean, this is awesome, chance to be here and meet the Denver community and see that it's growing. Probably how many years ago did this not exist?
Well, probably 3 months ago.
3 months ago, wow. So 3 months ago this didn't even exist, and you know, it's already quite an impressive size group, and I predict it's just gonna keep on growing. So congratulations on that, and let me know if there's any way I can help. So today I'm gonna be speaking about streams, and the topics I want to get a chance to cover today are first a brief primer on induction and co-induction. Because understanding these topics will help give you a better intuition for what streams are and what streams belong to. Streams actually belong to a broader class of things, of stream-like stuff, and having that insight I think is very, very useful for the long term. And I'm going to talk a bit about the fact that streams really show up everywhere in programming. I mean, in a lot of places. They show up in the front end and in the back end and in glue and middleware and sort of every layer of the stack. They're actually very universal. And once you have an abstraction that allows you to do streaming, you can use that all sorts of places that you never even imagined. Then I'm going to talk a bit about an abstraction from functional programming called CoFree. And don't let the scary name confuse you. CoFree may have a scary name and an awful looking type signature, but it's actually a fairly simple abstraction that lets you think about so-called co-inductive processes in a very elegant, very mathematical way. And I'll use CoFree to actually develop a lot of really interesting machinery for streams that you might find in any off-the-shelf streaming library. And then finally, I want to conclude with a little bit of a challenge, and this is great that this is a functional programming meetup because that challenge is for your skills as a functional programmer. I do want to point out that I will be using Scala for all the code examples. Scala is not the prettiest language in the world to look at. And if you haven't used Scala before, you may see, what the heck is that about? Well, if you've used something like Haskell or PureScript or Elm, then the way to mentally translate that for the most part is anytime you see hideous square brackets or parens, just rip them out, and then you get an approximation of what that would look like in Haskell or PureScript. And otherwise, if you're familiar with Java, then hopefully you'll be able to follow enough of the code snippets that you're not lost in anything. And I did want to actually translate this into a couple other languages. I just didn't have time, so bear with me. I'll explain anything. If you have any questions, feel free to just raise your hand. So, induction. Induction is the process of tearing down a structure to culminate in a terminal value. Induction is, in functional programming, induction is how we deconstruct data structures. For example, if we have a tree, then we can use the process of induction, for example, through recursion, to break that tree down into its component parts. And as we're breaking it down, we can look at every piece of that tree and we can see and observe its structure, and then we can do something interesting on the side. For example, if that tree represents JSON or XML, then we can use induction to tear down that structure bit at a time until we find the part that we're trying to extract from that XML document or JSON document and then return it. There are lots of examples of inductive programs, and one of them is just parsing a config file. So all of these are very batch-oriented processes in the sense that you start with some structure and you just sort of tear it all down until you produce the final value. in the case of parsing a config file, the config file is your data structure, it's your input, and you end up tearing it down and then building your separate data structure that represents the configuration of your application by parsing that. Sorting a list, that's an example of an inductive process. You have this data structure and you tear it down bit by bit, and what you're building on the other side of that is actually another list, but it's still an example of induction. Sending an HTTP response, that's another example of you have this big thing and then you tear it down bit by bit and sort of stream it over the wire. It's an example of an inductive process. And finally, computing the millionth digit of pi is an example of an inductive process. It may not be super obvious how that works, but you can actually sort of compute the millionth digit of pi either by computing all the prior ones, or there's even a super fancy way that you can use to skip that. And essentially what you're doing is carrying on this inductive process to terminate in that singular value, which is the millionth digit of pi. However, despite the prevalence of induction in all the problems that we face on a daily basis, I'm actually going to argue for the following, that most business problems are not inductive by nature. Rather, they're co-inductive. And you can contradict me on this if you want. Maybe I'm wrong, but I have lots of examples in my head of business problems that are co-inductive. But what is co-induction? So remember, induction is the process of starting with some initial structure and tearing it down bit by bit and culminating in some terminal value. You can think of co-induction as the exact opposite of that. So we start with some initial value and we sort of unfold that to build additional structure and more structure and more structure and more structure in sort of a stateful way that allows us to almost reverse the process of induction. That's why it's called co-induction, because it's in some sense sort of the opposite. If you're standing in a mirror, you'll see induction on one side and co-induction on the other. They're mirror images of each other, categorical duals, if you will. Let's look at some examples of co-inductive processes to gain an intuition for what this is. So one would be producing the next state of a user interface given a user input. There's the Boulder crowd, yay! You put in a showing. It's the traffic, I know, it's the traffic. So producing the next state of the UE given a user input. So we have some state of the UE, and then we feed it the user input, and we get another state, and we feed it another user input, and we get another state, and sort of the input that we feed it ends up determining, in some sense, the direction that we end up unfolding that state. And so we conceptually, we can think of this as a co-inductive process. Or how about the example of the config file? Well, it's easy to view parsing a config file as an inductive process, but we can also imagine that what we really want it to be is a co-inductive process. That is, we want to produce the current state of the configuration for our application given an update to the config. Because how many of us have ever wanted to update the port number or update some bit of configuration to a live running server without having to restart it? Ideally, that's how all software would always function. We would just be able to do that. And we can't do that because essentially we've modeled what should be a co-inductive process as an inductive process and sort of get into the limitations of that. Another example of a co-inductive process is transforming a stream of requests to a stream of responses, which sounds a lot like a web server, right? You have this endless stream of requests hitting your server, potentially endless, and you're simply transforming them to output responses to the clients that originated the requests. And finally, computing the millionth digit of pi might be an example of an inductive program, but computing all the digits of pi, sort of as this infinite stream, that's an example of a co-inductive process. So you can see here a couple things. Hopefully you have a little bit of intuition for the difference between induction and co-induction. But hopefully beyond that, you can see that a lot of the problems that we actually solve using induction would make lives so much easier on end users if we solved them using the power of co-induction. And I think there are lots of reasons why that doesn't happen. Mainly because programming languages hate co-induction. They really do. I mean, what are our programming languages? They allow us to build these, they start out with a main function, which does what? It accepts some input and then it returns a value. It's fundamentally inductive. Unless you want to like, read standard input and write standard output, which would be the equivalent of more co-inductive process. But most programming languages don't have features to natively support co-induction, even though that's to some extent changing a little bit. Has anyone heard of generators in JavaScript in the latest Java? Yeah. So suddenly they've added a construct into a language to specifically support co-induction, which is interesting, but most programming languages haven't gone that far. So, however, despite all of that, you've probably heard a lot of hype surrounding reactive programs. How many have heard that terminology, reactive programs? So almost everyone has heard that. So that's, yeah, a lot of hype around reactive programs. And UEs can be reactive, and server systems, actor systems can be reactive, all these sorts of things. Reactive are ways of co-induction leaking into our everyday programming lives in the form of libraries that make designing these sorts of processes a lot easier. And then, of course, the topic of this presentation tonight is streams, and streams are fairly big, maybe not as big as reactive yet, but there's a lot of emphasis going into streaming architectures, especially in data processing and big data, and to a lesser extent in the front end side, streams everywhere. And that's an example of co-induction starting to leak into our everyday worlds of inductive programming and hopefully make it easier for us to build the kinds of programs that we want to build. So a stream is a mainstream example of a co-inductive process. It's not the only type of example you can imagine, but it's a really good example because we can get our heads around a stream. We've probably all used streams. And you'll find uses for streams in data processing. You'll find uses in web servers, in user interfaces, in discrete functional reactive programming, and so much more. Really, there's so many applications for streams, you can't even enumerate them. What are the characteristics of streams? Well, they're stateful. So as that stream is sort of processing along and spewing out stuff, subsequent things that they spew out can be dependent on prior things that they generated. Example of that is a stream of all the digits of pi. So the emission of one digit of pi, of course, depends on the state of having emit all the preceding digits of pi. So streams are stateful things by nature. They also allow you to do incremental computation. And they're very, very good at doing incremental computation. So you have some initial state and a stream, you'll send an event inside that stream. Like maybe it's a user input, or maybe it's a patch to a data structure, or maybe it's a chunk of new data. And you'll use that stream to incrementally process something and produce some output. Streams don't necessarily terminate. A web server, for example. A web server will, assuming you have no bugs, which is probably not true, a web server can run forever, right? And the millionth, or the example of all the digits of pi, that's a stream that never terminates. So streams are, you shouldn't think of streams as a list, you should think of them in the general case as being infinite. And to be useful, of course, streams need to be able to consume things from their environment and then emit them on the other side. So streams suck in information, whether that's by reading from sockets or reading user input events in a DOM or whatever it might be. They consume information and then they emit some other form of information now on the other side. Well, in the world of Scala, you have lots of options for doing stream processing. And I'm sure in whatever programming library of your choice, there's probably a handful of different libraries you can use if you want to do some kind of stream processing. In Scala, there happens to be Akka Streams, which is probably the most popular. Java Streams, which is fairly new, much more simple, but also much more limited. Scalaz-streams, which my company uses. FS2, which is a successor for Scalaz-streams. And then you have the big data stuff, which is sort of its own bucket and its own runaway bucket of competing stream technologies, ranging from Apache Flink to Spark streaming, Pachyderm, Kafka, and just on and on and on and on. So many different streaming abstractions over there, you can't even count them. So I'd like to give you some insight into the way I evaluate libraries when I'm trying to choose one to use in an application. These might not be helpful for you, but if you think like I do, if you reason about code like I do, if you're a functional programmer or aspiring functional programmer, then these guidelines may help you choose better libraries. So what are they? Well, first is reasonability is directly proportional to totality and referential transparency. So what does all that gobbledygook mean? Well, it means something actually quite simple, which is if you have some library out there, and that library is a collection of functions, and these functions take some input and return some value, and no matter what input the compiler allows you to send to that function, it will return a value. And not only that, it will return the same value for the same input, then that helps you reason about the software. Does that make sense? If a function always gives me the same value for the same input, and if that function can accept all values that the compiler allows me to send to it, pretty simple to reason about that, right? And it's pretty simple to test it. And then it's also pretty simple to stitch that function together with other functions to build more complex functions that do more things. And that's the essence of reasonability, and it's quite honestly, it's the number one reason why I'm a functional programmer, because it just helps me reason about software better when everything is a total referentially transparent function. Composability is inversely proportional to number of data types. What does that mean? Well, in dynamic programming languages, you can sort of smash everything together. And sometimes it works, and sometimes it doesn't, and you'll discover that at runtime. But in statically typed programming languages like Java and Scala and Haskell and so forth, you can't smash everything together. You can't feed everything to any kind of function. They have different shapes, and sometimes they don't always fit together. But the more unique data types you have in any library, the less things are going to fit together. So for example, if you have a library that has 100 or 1,000 different data types, what are the ways in which you're going to be able to combine these things together? Your odds of being able to combine them together are not very good. So basically the way in which the library is designed, it will be designed as either a monolith that tries to package in 1,000 solutions to your problems, or it will be designed in more Lego fashion, giving you building blocks that snap together, from which you can assemble a solution to any problem. And when it's the latter, we say it's composable, and generally that correlates with a relatively small number of unique types. The third law is obfuscation is directly proportional to the number of lawless interfaces. What does that mean? Well, we've all been in the situation of most likely having some interface or some protocol or some trait. Different languages call them different things. And it has all these different names in it, methods. And maybe they have types, maybe they don't. And there exist lots of different implementations of these. And every single implementation does something slightly different. And the reason why that's hard to reason about is it's a uniform interface, right, in theory. But if that interface, if the interaction between those different elements in the interface is not governed by any sort of reasoning principles, if you can't say calling this one is equivalent to calling this one followed by that one, if you can't say deleting this file is the inverse of creating this file, if you don't have those abstract reasoning properties to give you guarantees on what that interface does, then by definition you have no guarantees. And your only guideline is sort of the name of the function, you know, the name of the method. And maybe that's enough to help you understand it well enough to write code, but oftentimes in my experience we assume one thing when something's named one way and we use it and then it yields different behavior entirely. And then when we plug in a different implementation of that same interface, we end up with different behavior altogether. And that's an artifact of interfaces that have no laws, that permit no generic capability of reasoning across the way these different methods interact with one another. And that is obfuscation, because it makes our job as developers much, much harder, because then we have to figure out by exploring and playing around, and every different implementation of that interface might do something differently. The fourth law is correctness is directly proportional to the degree of parametric polymorphism. So if you program in dynamically typed language, ignore that, because it probably doesn't mean anything. But if you program in a statically typed programming languages that has parametric polymorphism, for example, Java generics, or Elm has this, and obviously Haskell and PureScript and lots of languages have this feature, then what that basically means is when you're declaring a type of a function, the function itself can be passed a type. In other words, it can operate on any type at all. And when you use parametric polymorphism in a statically typed programming language, the compiler doesn't know anything about that type because your function can work with all possible types. And that may seem like a crippling limitation, and in some cases maybe it is, but it's also a killer advantage because you can't screw up a type if you don't know anything about it. If there's nothing you can do with it, then there's nothing you can do with it. And this leads to this principle that, number 4, the law that basically states the more ways there are for you to implement a function given its type signature, the greater the probability of a defect. And highly polymorphic code, that is code that knows very little about the types that is passed in, tends to have way fewer implementations. In fact, some of these functions, not very common, but they do exist, only have a single implementation. You describe the type. An example is a function that can operate on all types A, which takes an A and returns an A. What is the implementation of that function? Identity. It can't do anything else. Or a function that operates on all type A's and all type B's and takes 2 of these things, an A and a B, and returns a B. What does that do? Returns the second element of that. So that's amazing. Like, that's amazing that parametric polymorphism can constrain our functions to such a degree that they can cut down on the number of ways to implement them. And if there's fewer ways you can screw things up, then you're more likely to get it right the first shot. The 5th law is that shoddiness of a library is directly proportional to its encapsulation. So what do I mean by that? Many of you are smiling because you know what I mean by that. You've been through that. But the basic gist of it is that sometimes as programmers, we have to do some nasty, nasty things. And we're paid to do nasty things. We're paid to ship code. We're paid to solve problems, right? I'm not complaining about that. I mean, maybe I am complaining about it, but it's something we have to do. But the more nasty things you do, you obviously don't want to expose those nasty things to the users of your code, so you encapsulate them. You hide them. You hide data types. You create private methods. You stick implementation details far deep inside there. That's because you don't want those escaping to the outside world. They're way too nasty. And if people see that, they'll be confused. If they use it, the code will go wrong in horrible ways. And so, the more encapsulated a library is, the greater its shoddiness. That is, it doesn't have stable foundations necessarily. It may happen to be correct because it's been through lots of testing, and it may be some gnarly code that we never want the outside world to see, but we may know it's correct because we have all this test. But in general, libraries that lets you peek inside and see everything and use everything, those are built on solid, stable foundations that you can count on. And the ones that hide a bunch of gnarly crap inside there, they tend to be much more shoddy. And then the last law of clean functional code is the volume is inversely proportional to the orthogonality. And I already gave this one away when I said some libraries make the choice to expose this monolith API that solves 1,000 different problems. And others don't choose to solve any problem. They just give you 10 building blocks that you can combine together to solve 1,000,000 different problems. And I've found that which one I prefer has varied over the course of my career. And it also varies with the level of investment that I want to spend on a given task. So if I have to use this language, which I hate, to solve this problem, which I really don't want to mess with, and it has to be done by this almost impossible date, please give me the monolith. Because I'm going to use the monolith, and I'm going to find my one method on there, 2 methods on there that does the thing that I wanted to do, and I'm going to call them, and I'm going to ship it. I'm going to hope I never have to deal with that problem again. But on the other hand, if I want to invest in something, and I want to understand it, and I want to be able to maintain that in the face of ever-changing business requirements, then throw that monolith in the trash. Because I don't want to have to learn its thousands of methods. I don't want to have to work around its limitations. I don't want to have to know how all these different things interact with each other. I want 10 things that I can keep in my head, whose behavior is well-defined, that compose together in logical, sensible ways that allow me to solve the problem I have today, but also allow me to solve the problem I'm going to have next week, and the month after that, and the year after that. And that's the essence of composability. Orthogonality. And it's inversely related to volume. The more orthogonal those features are of that library, the smaller space it can shrink to fit into. So let's use these laws to take a look at the most popular streaming library for Scala. I'm just going to show you a little snippet. So, can anyone venture, why might not we want to use Akka Stream? This is a package dump. It shows all the types in akka.stream. It's big, right?
Are you cheating a little bit here just because Scala can't abstract over rarity?
Yes, be quiet. Nonetheless, with applicatives, you can abstract over rarity, so I'm not really cheating. Maybe a little.
No, I've written plenty of
So, okay, maybe in some cases, this is what you have to work with because it's been decided for you, or it just has the feature set that you need. But this is a lot of complexity, and it's a lot of complexity that's not necessarily inherent to the problem. So, what if I told you we could have a streaming abstraction that satisfies all these laws? A streaming abstraction where everything is total, everything is referentially transparent, where there's only one data type, and therefore which it composes with itself in a huge number of ways. There are no lawless interfaces. Any interface in there is just a standard part of our toolkit as functional programmers. It's super super polymorphic, such that most of the methods only have a few ways to implement them, so it's really hard to get them wrong. If you had to hide nothing, you could expose all the guts of this thing without having to worry about any of the ramifications of doing so. And if you could fit it all in a few hundred lines of Scala code. Well, you'd probably say I was crazy. And indeed, I am a little crazy because I'm not advocating this as a functionally equivalent version to Akka Stream. But nonetheless, there is an abstraction in functional programming that lets us have all of these benefits. And it's called cofree. If you've heard of the free monad, anyone heard of that? So yeah, a few people. If you've heard of the free monad, again, big scary names, but free monad is basically a very complex name for a relatively simple idea, which is, what if instead of executing assembly, which is basically what we do when we call print statements and read from files and read from sockets, we were to instead build a data structure that described our computation. It would describe the fact that it read a line of input and wrote a line of output and so forth. That's incredibly powerful. But what that is the essence of the free monad, is describing effectful interactions with the real world in terms of a data structure. And once things are a data structure, you can transform them, you can introspect them, you can do all sorts of amazing things like mocking in a wonderfully safe, very clean way. But that's a topic for a different presentation. I'm not going to sell you on the free monad, but I will say, for those of you who've heard of the free monad, that cofree is basically the co-inductive equivalent of the free monad and has similar types of benefits to free does in inductive programs. It looks a bit like this. And again, I apologize, it's Scala, so it's pretty hideous and a little hard to decipher. But the basic idea is this: it's a data structure, and that data structure has a head and a tail. And we say a cofree of F and A is a data structure such that the head is an A. Which means if we have like a cofree of F and int, then the head of that data structure would be an integer. And in this presentation, we would be using that to represent a stream of integers. And then it also has this thing called a tail, which you can think of as an F-shaped container. So it's an F-shaped container. And that contains another cofree of F of A. So this is a so-called co-recursive data structure, or recursive data structure.
How does this differ or relate to like a cons list?
So a cons list, you can actually model a cons list quite nicely with cofree. And how you do that is you substitute option or optional or maybe, whatever it's called. It's the type representing optionality in your FP language of choice with F. So for example, a cofree of option and integer is basically a cons list of integers. Let's see if we can figure that out. So cofree of option of integer. So what does that make the head? An integer. What does that make the tail? Yeah, an option of another list. So either that option is nothing, in which case it only had a single A, or it's sum of basically another one of those things inside there, in which case when we extract out that sum, we're going to find another A, and we can keep on going through that process. So it's actually a non-empty list rather than an empty list, but it's almost the same as a cons list. It does? Good. So let's do another example then. Has anyone heard of a future or promise? Okay, great, super. Okay. Let's say because a promise is like a container of something, right? It's a container of the value that it promises to produce at some point in the future through a synchronous code or callbacks or whatever. Let's say we have a cofree of a promise of booleans. What does that tell us? The head is what? Boolean. And what's the tail? Well, it's a promise of basically the rest, the remainder of the cofree structure. And what does that do? It lets us access that first Boolean right away. And then it says, well, it promises it's going to do some async computation, and eventually we're going to get access to another Boolean, as well as the remainder of the computation. Does that make sense? Starting to fit together? You don't have to pay attention to the details. The big picture is there's that head, which is an A, and then there's that tail, which is wrapped in the F. And this F is technically it's a functor, and that means it's this mathematical abstraction. Basically, you can map over it. So like lists you can map over, and options you can map over. It's the set of things you can map over sensibly without changing the structure of the thing. All right, so let me give you two intuitions for thinking about a cofree. A cofree of f of a is a co-inductive process that generates a's using effect f. In one case, we looked at the effect of optionality, and we saw that cofree of option of a is equivalent to a non-empty list of a. In another case, we looked at the effect of asynchronicity, where f was a promise or a future, in which case we've got this chain of asynchronous computations that at every step yields an a. There's another way to look at a cofree, and I actually really like this one. And that is a cofree of f of a is a current position a on an infinite landscape that requires effect f to move to a new position. So think in your minds this big infinite landscape, and we're located right now position A, and we can choose in which direction we want to go, but in order to get there, in order to get to a new position, we have to perform some effect f, whether that's optionality or asynchronicity or IO or whatever is represented by f. And I like that for the following reason. Cofree forms a comonad. And you don't have to remember that terminology, just keep in mind you can map over the A's inside a cofree. That means if you have like a cofree of booleans, you can map the boolean to an int to get a cofree of ints, and so on and so forth. So you can map, you can change what's inside that cofree. The values being emitted by that cofree, you can change them by mapping over it. But also, you can tell where you are. And the method or function that lets you do that is called extract. Given a cofree of f of a, it's going to tell you where you are by, of course, extracting out the head. And then you can terraform the landscape. This is maybe a bit strained terminology, but it almost works, which is the process of, given a cofree of f of a, if I have some way of turning that into a b, then I can turn the whole cofree of f of a into a cofree of f of b. You can view that as sort of lifting up the landscape to a different level.
Isn't extract some kind of unapply or John, could you repeat the question?
Yeah, say it again.
Is it extract something like decomposition of existing cofree, or because it's basically like a signature, it should be like a signature of the cofree itself?
Exactly. So, well, actually, these are, yeah, the extend function should be a method on a cofree. That is, for any cofree, you should be able to call extend on it. All right, so play around with these methods sort of at your leisure. I'm not going to use them much, except I think maybe in the implementation of some of the stuff. But that's basically what these comonad methods allow you to do on a cofree data structure. So let's prove to ourselves that we can actually use this to represent an infinite stream by creating a cofree representation of the Fibonacci sequence, which is infinite. The Fibonacci sequence is just 0, 0, I think it is. You can correct me if I'm wrong. 0, 1, and then you just add every 2, to produce the next one. So 0, 1, 1, 2, 3, etc. So let's do that. First, we need to choose an f. So for f, we're actually going to choose a lazy container called name. This is part of a library in Scala called scalaz. But you're going to find something equivalent to it in almost any library. And if you're an old C programmer like me, we used to call these things thunks back in the day. So we're choosing f to be this lazy container whose contents are not evaluated until you force them to be evaluated. Why would we want to do that? Anyone have any ideas?
We want to eagerly attempt to generate all of the Fibonacci sequence.
Exactly. We don't want to eagerly attempt to generate all members of the Fibonacci sequence, right? That's not going to be good for our computers. So what we want to do is use a lazy data structure that's not going to do any work until we force it, and then it's going to do the minimal amount of work necessary. So in our example for Fibonacci sequence, our f will be name, which is this thunk, which doesn't generate the a. It's like, think of a thunk as a function from unit to the value that's being produced. So you send it unit, and it's going to give you back the value. And we do that with that simple unfold function, relatively simple unfold function, which takes the 2 previous integers and bundles them up in a cofree by summing the 2 previous integers and then calling itself recursively, but protected by that lazy data structure called name, so it's not going to actually call it recursively, it'll be evaluated lazily. And then we handle the initial case. And this gives us a stream of all the Fibonacci numbers. So very simple, but it should at least prove to you, okay, yeah, you can use cofree to represent an infinite stream because, hey, we just did it. All right, so another fundamental operation is if we have 2 streams, and at least the first one of those is finite, they don't both have to be finite, but if the first one of those is finite, then one of the fundamental operations we can do on streams is to append them. And that just means generate all these, and then when you get to the end, generate all the rest. And here's a 1-line implementation of append, which uses some stuff that I'm not even going to go into necessarily. But here are the key things to note about this. First off, we didn't have to invent any new interfaces. All these things are standard tools in the toolkit of functional programming. In this particular case, they're all in scalaz, but if you're using a different functional programming library, they're going to be in there. They're standard tools. We had to invent nothing, and yet we're able to take any 2 streams and append them, given only a single constraint, which is we need a little bit of additional structure on that f. It can't be just any f. It has to have the structure of this abstraction called applicative plus, which I don't want to go into now, but among other things, it allows you to take an f of a and an f of a and add them together in such a way as to produce another f of a. So if we're going to be using these things, cofrees as streams, it would certainly be nice if we could pump one for all the elements. Now for infinite stream, of course, we'd...
Can we back a step? I'm curious actually about the applicative plus operation here. Because you're using C2 twice. In one case you're, C2 being a, it's a covert structure. So you're appending it within the map over the tail of the initial stream, but why are you then using applicative plus to append it again?
The intuition is, if the first one's empty, then return the second one.
So what is point then?
Point is an operation for any applicative plus that allows you to take an A and lift it up into an f of A. For example, it could take an integer and lift it up into an option of integer, or take a Boolean and lift it up into a promise of Boolean.
Should that actually be applicative plus and not alternative?
So I believe in Scala-Z, this is the right version to use. If I were using pure script or Haskell, I would use alternative. Yeah, that confused me too. I couldn't find an alternative, and apparently I believe this is their equivalent, but it does the right thing, and you can test it. So if we're going to use these things as streams, it'd be awfully nice if we could take and pump a stream for values, maybe just for testing. Of course, we'd never want to do this on an infinite stream, but it'd be nice if we could pump them all and stuff them into a list, just so we could inspect them. And that's the method there called collect, which requires additional structure on F. It has to be something called a monad plus, so it's a monad that supports an additional operation called plus. But if you have that, then you can implement this collect method that basically pumps all the values out of the stream and stuffs them into a vector, which is just basically a data structure. It's basically a list, but it has different performance characteristics. And then there's an inverse of that, which is if we have some sequence of A's, can we turn that into a stream? And the answer is yes. We just need to require that F be applicative plus, and then that's the implementation for that.
How we can collect potentially infinite stream?
Right, so how would we do an infinite stream? So in Scala has an abstraction called stream, which can model infinities. And we could write a function which would convert a stream into a cofree. We could do that. And conversely, for infinite, if we wanted, we could write the collect function to return a stream as well. Can anyone tell me why disperse here returns an option of a cofree and not a cofree? It's kind of inconvenient to get an option back.
Sequence might be empty.
Yeah, sequence might be empty. And cofree always has an A, right? It always has some A in it. So we can't just return a cofree, we have to return an option of an A because the sequence might be empty. But you could write another disperse method if you wanted that would only work with non-empty lists and could actually guarantee that it could always return a cofree. Okay, so here's another one, zipping. So we have two cofrees representing streams, and we zip them together. Well, all we need for there is that F be a functor, so you can map over it and preserve the structure, and it to be a zip. And a zip just means you can take an F of A and an F of B and zip them together to get an F of A and B. So for example, if you have an option of A and an option of B, you can in fact zip those two things together to get an option of A and B. If you have a promise of A and a promise of B, then you can in fact zip those together to get back a promise of A and B, and so forth. Lots of these F-like things, lots of these container-like constructs support that zip operation. And if it does, then you can take those streams and zip them together. And then I think the last of these basic methods that I'll cover is an operation called scan. Scan lets you start with a state and then pass a function that can update the state, basically return a new state given the old state, as you're feeding it the A's of the cofree. Does that remind you of anything? What?
Fold.
Yes, fold, right? Does it remind you of fold a bit, right? Because when you're folding over a list or you're folding over another data structure, you start with your initial state value, and then fold is going to rip off pieces of that thing, and it's going to send every piece to your function, which can then compute the new state, given the old state in the piece that you ripped off, and then the fold function of the list or whatever you're folding over, it returns the final state. So scan is basically the equivalent of that, but note that it doesn't actually return an S. It doesn't return the final state. It returns, rather, a cofree of F and S. So as you're sort of scanning over this and maintaining state, this scan function is returning this cofree that spits out new state values. It doesn't return a single final state. Why is that? Say again?
You observe every intermediate result.
You do observe every intermediate result. Why would the other type signature be unsound in the general case? Or unsafe, I should say. If we were to change this scan function to be a real fold and return an S rather than a cofree of F and S, what could go wrong? That probably would. Infinite sequence. Fibonacci. Let's fold over the Fibonacci sequence to produce something, right? And then that of course would blow up. So we can't make that guarantee, but we can make the guarantee we can, like, produce a process, a cofree of the sum of all the Fibonacci numbers, and we can keep inspecting later and later values of that sum, but of course there's no final sum because it would be infinite. Oh, and it looks like I've got filter as well here. So if we have a stream, we want the ability to kick stuff out. And there's two ways we can do that. We can do it in a structure preserving way under the right conditions. If the elements of the stream can be annihilated, zeroed out, then we can preserve the structure of the stream and we can just zero those things out. For example, if we have a stream of options that produces these options of ints or whatever, then we can filter that by just turning every option we don't want into a none. Or if we're doing analytics, then for many analytics, all we would have to do to have no effect on the result of the sum is turn something to a 0. Or if we're doing a product, we could turn it to a 1 and so forth. So that's the zeros function, and it allows you to filter stuff assuming that the A's form a monoid, so there's a 0 for that, and you can smash two A's together to get another A, and assuming that F is a functor. If you make that constraint on F more powerful, however, if you turn it into a full-featured monad, so if it has all additional structure, then you can actually delete stuff from your stream, and you can actually change its length. You can change its structure, but you do require that additional constraint that F be a monad. And it is for promises and options and lists and tons of other things. It is in fact a monad. All right, so that's it. That's basically a mini library that uses cofree as streams and allows us to do all the sorts of things you would expect to be able to do on streams, like appending them and zipping them together and scanning over them and filtering out stuff that you don't want. But it's still not a full-featured solution to our problem, because remember, many of the streams that we encounter in real life, they take some input and they spit out some output. Like they take a user input and they spit out the new state of the UI. Or they take a request and spit out a response. Or they take a patch and spit out a data structure. And we can't do that with the machinery we've built so far. We can still use the machinery we've built so far because we've placed minimal constraints on it, but it's not enough. It's not enough structure for us to be able to feed these things values and have them transform them or manipulate them in some F-effectful way to produce an output. And to do that, we need to introduce a bit more structure. And that bit more structure is represented on this slide. There is an abstraction called a scalaz-stream. And a scalaz-stream is basically just an effectful function. So a scalaz-stream of f of a and b is a function that takes an a and returns an f of b. So think of f as being an option, in which case f represents the effect of optionality. So this scalaz function, it's an effectful function. We're going to feed it let's say a string, like parse string to int, right? That's our function, is to parse string to int. We're going to feed it a string, and our effect is optionality, and it will return an option of an int. Why does it return an option of an int? The point of the function. Yeah, right. And the string, the contents of the string might not be parsable to an int. They might be foobar blah, blah, blah. In which case, what integer are you going to sensibly produce out of that? There's nothing you can do with that. So scalaz of A and B is an f-effectful function that takes an A and returns that B inside an effect. Where that effect could be a promise, it could be optionality, it could be many more sophisticated things. You can think of it in concrete or abstract terms, but in essence, scalaz models an effectful function from your average imperative programming language like C or Java or whatever. It's just an effectful function that takes an A and returns a B. And in order to actually get access to that B, you have to perform some F effect. So given this scalaz abstraction, it's actually rather simple to build what I call a pipe, which is a stream. You feed values in, you feed values into one end of the pipe, and you get values out, and it can perform F effects along the way. How do you do that? Well, remember that F structure that a cofree needs? Well, instead of it being option or promise, it's going to be a scalaz of F and A. In other words, it's going to be this effect is going to be the effect of a effectful function. And an example would be, let's say our scalaz, well, actually, let's use the previous example that we did, the case of parsing a string to an integer. So we can imagine a pipe whose F is option, whose A is string, whose B is integer. That represents a process which reads strings and outputs integers. Until it finds the first one that it can't parse. Yes. Limitations of that preceding example. Okay, so if that's a pipe, that is, if a pipe is this cofree thing that, if you want to expand this in your mind, it's helpful to understand these things if you expand them, like either paper or code or whatever. Remember, you can do basic substitution. There's nothing fancy in substitution. And as a aspiring functional programmer, I've been forced to become very good at substitution, mental substitution, but also, and that fails, which it does often, just typing stuff out and substituting it to see what I get. And that's a really interesting property of functional programming, is to understand the meaning of something, you just substitute the symbols. And what you can do here is just substitute scalaz FA question mark for the F in the preceding example, and then you get back that cofree example where the A is or rather where what I'm calling a B here is in the head of the cofree. That's the output of the cofree process. And what that F is it's just a function that's preventing you from getting access to the next cofree until you feed it an A. Because remember, it's a pipe. So it's not going to let you have that next cofree until you feed it an A. And when you get the next, when you have an A to feed it, then you can get the next cofree out of that, and you can continue the process of pumping this pipe for B's given a steady supply of A's. So how can you model sources and sinks? Well, a source is just something that produces A's, and a sink is just something that accepts A's. A source requires nothing to produce an A. You can literally produce these things by feeding it unit. It has no requirements. Anyone can synthesize a unit because there's only one such value. So you just feed it that and you can produce as many A's as you want. And same way with a sink. A sink is just a pipe that you feed it whatever it accepts, that A that it accepts, and it outputs unit. It outputs no information. You feed it those A's purely for the F effects, because you're not going to get anything out of the other side, anything useful. You won't get any information out of the other side. Okay, so given this definition of pipe, what are a couple fundamental things we can do? Can anyone guess what sorts of functionality we might need based on these type signatures in order to usefully use these pipes?
I'm reading the slide, but I imagine compose pipes together.
Exactly. So we have two pipes. This one takes A's and outputs B's, and this one takes B's and outputs C's, and we would like to be able to compose these together to get another pipe. And you can do that in the implementations that one-liner, which again, if you don't know Scala, is not going to make any sense at all, but it is actually relatively straightforward with minimal requirements on the structure of that F. You don't actually require a lot to be able to pipe these things together. What's another thing we might want to do here? After we imagine we're building this application or this UI or server or whatever, we're connecting all these pipes together and on and on and on, and we keep on building up more pipes, and we end up with a pipe. What do we want to actually do? Execute it. Exactly, and that's the run pipe function. So typically you would have in order to call this, you would have a pipe of F and unit. And that just means you feed this thing unit and it produces unit. In other words, you've connected a source to a sink. You've connected a source to a sink, and now it requires no information to get this thing running, and it outputs no useful information. So it's basically a completed pipeline. And you can run that thing. All it requires is that the F be a monad.
I have a question. So I guess I'm trying to understand why we need this scalaz-stream machinery in contrast to using the scan method that we created before, where S was an effectual thing. And because I could imagine you could compose two scans together, I guess, can you clarify why scan is insufficient and why we need this machinery?
I think that's a really good question. I think it's probably not required, because as you scan, you build up additional cofrees, and eventually, in the end of the world, you can output those using some type of F, maybe not the one you started with. So you probably don't need any additional machinery, and that actually looks a lot like closures transducers. Or Haskell has this library called fold-L.
So I think the one thing there is that you're not, I think that you would end up using some.
I don't know how you would combine.
Lose the composition property, right? Because with pipes, you have this type constructor F, which represents your effect as you're taking each step through the cofree process. But you don't, in the scan case, you don't have that type constructor, and so you can't write pipe.
You can compose the fold functions together, the SA to another S, but it doesn't seem like that would be quite as expressive for the case of multiple streams. For a single stream, it might be equivalent. What do you think?
In the sense that you can kind of construct a pipe and pass that around in a first order manner and operate on that, whereas if you have a stream, you can't sort of prepend anything to the logical beginning of that stream.
Exactly.
If S is some effectful type, how do you actually observe those values? I'm not sure if you can peek inside those individual values as you're working through the process.
Yeah, I'm not sure. I think if you push that, you would end up with either closures transducers or Haskell's fold-L or something equivalent. I don't think those things are quite as composable as streams, because streams, you can merge things together and you can split them and you can do all these sorts of things. But that's a good question, actually. All right, so how would we model I/O streams or byte streams? We don't need any new machinery. All this machinery that we've already built can handle any type of stream you can imagine. An I/O pipe is simply a pipe where that F represents an I/O effect, which is labeled differently in different languages. A pipe that operates on arrays of bytes, in other words, a binary pipe for pumping binary data, is simply an I/O pipe of array of byte, and so forth. And these things just sort of compose however you like. Okay, so there's two more things I want to show, and then that'll be it. And this is just to demonstrate that you don't have to stick with the simple stuff. You can actually start to build some of the more complex compositional machinery typical in streaming libraries. And one of the classic cases here is I have two pipes and I want to merge them together into a single pipe. So how does that work? Well, this is one way. I don't claim it's the best way, but I was actually surprised it needed no new machinery in order to do this. All you have to do is use this thing called a coproduct functor, which I've given a type alias called select. And the only takeaway that you need from this type alias called select is that select allows you to say, I want to read from the left pipe, or I want to read from the right pipe. Because you want that to give it, you want it to have control, right? If it's reading from two files, then it needs to be able to like read so much from here and then make a runtime decision to read a variable amount based on what it saw in there. So whatever thing is merging these two pipes together needs the ability to decide which one it's reading from. And so you just need this little selector that can either be a left or it can be a right. And then you define this thing called a merge, which is a particular kind of pipe that can choose its input. And then the actual merging function is, if you ignore all the types, if you had type inference, this would be really simple, but it looks complicated because you have to state all these types everywhere, or at least I did. What this merge function does is you give it a left pipe and a right pipe, and then you give it this, this thing which can decide which one it's going to read from, basically a pipe that can choose its input, and then it can smash all those together to give you, well, it can smash you give it a left source and a right source. So these are things that are producing, one is producing an A, one is producing a B, and then you give it the pipe that can choose whether it gets A's or B's, and you can merge that together to get a source of B's.
Can you show the select signature again?
So in this particular variant, it has to read the same type from either the left side or the right side.
I was just curious about your user ID in the implementation.
Okay, so there's a little bit of complexity in this function, which I just wanted to leave in here because it's more general, and that is the source needs to be able to describe which one it reads from first, if that makes sense. Like, it needs to either say, I'm going to read from this one first or this one first, and once it starts that process, then it can describe, based on whatever information it reads, which one it's going to read through. But the way that manifests as additional complexity here is what you're passing in is basically a left of this machine that's going to read from either side, or a right of this machine that's going to read from either side. And so you have to deal with that with this embed mechanism, which uses the identity functor. I'm sure you could find some other way to write this. It's what I had time for. It was my 15-minute solution. Forking. Okay, so this is really interesting. Notice sort of the duals here. You can take two sources and something that can read from either, and you can combine them together to get another source. So that gives you composability in one direction, because you can imagine the graph of all these streams, merging in, and basically this gives you the ability to compose any number of sources, no matter how many, into a single source, if you have processes that can determine which one they want to read from. But what's the opposite of that? exactly, splitters. So given a sink of f of a and a sink of f of a, give me another sink of f of a, such that I send it an A and it's going to split off into each of the two sinks. So it's the reverse of the other one. And then something really cool, I have no time to spend on it, but we've been thinking about F as being something like option or promise, or maybe IO monad or something like that. But you can actually think of F as being a product. And this product has many different choices available to you. And you can choose which one you want. And how do you model that? Well, your F, in this case inster, becomes this literally a product type of different options. And in this case, I have go left, go right, go up, go down. It's just nonsense. I couldn't think of a more realistic example. But, and then you define a cofree of this instruction, which can then use another effect called F. And what does this give you the ability to do? Well, it's really, really interesting. It gives you the ability to send messages to your machines constructed with these cofree processes. So you can tell them to do things. Not only can they read inputs and emit outputs, but you can tell them to do things. You can direct their behavior. And this corresponds again in cofree, remember? Cofree is, where am I? That's the head. And where do I want to go? That's the F. You may in your mind think of F as being a single thing, like an option, but really that can be a massive product of lots of different choices. And I can choose where on the landscape I want to go next. And to get there, all I have to do is execute an F. So this is really, really interesting. And these things compose very, very well in the sense that if you have a cofree of F of A and a cofree of G of B, and you have some way of combining an A and a B into a C, then you can get back a cofree of a product of FG that produces Cs. Which basically means you can take this machine over here that accepts one instruction set, and then you can, in this machine over here that accepts a different instruction set, and you can combine them together into a machine that accepts both instruction sets, which is really cool. All right, well, that's cofree. That's an experiment in cofree. And I hope that it has, if nothing else, demonstrated there's a lot you can do without introducing new interfaces, especially new lawless interfaces. There's a lot you can do without introducing new types. There's a lot you can do just leveraging existing machinery inside of functional programming. We've basically recreated a mini stream library, and would I recommend you take this out and use it in production? No. And in real life, are you going to be stuck with Akka Streams or something else? Probably. Probably so, sorry. But I do want to give you all a challenge. And that challenge is not to go home and master cofree and all this other stuff, you know, monads and applicative plus and whatnot. But it's rather to be inspired by this idea just a little bit. It's to go home and it's to try to write code that's a little simpler than before. See if you can distill down the essence of a problem by removing information on what you know about types, for example, or by cutting down on the number of your building blocks and making them so they fit together better, or cutting down on the number of interfaces that you make that are totally lawless and difficult to reason about. Just do one thing. So pick one thing, take it out into your production work, and maybe it's a small thing, but small things add up, and small thing plus a small thing is a big thing. So I would challenge every one of you here to, if nothing else, take home the message that software does not need to be gigantic and complex and impossible to reason about. It can be simple little building blocks, and even if we don't understand all of this stuff now, we can take that idea back home with us into our job and write simpler software that's easier to reason about, easier to compose, easier to test, and easier to change safely, which is going to help us. All those things are good for us, and it's also going to help the business. The business will appreciate that a lot too. So that's it. If you've enjoyed it, follow me on Twitter at JDGoes, and don't forget LambdaConf 2017 is happening, and it is literally just up the street, well, up the road, up the diagonal. Boulder, May 25th through 27th, and we opened registration today. So if you love functional programming, if you want to learn more, there's going to be lots of stuff for beginners and experts and everyone in between. So hope to see you there. Thank you very much. Yeah, so this year there's going to be at least three workshops, commercial workshops beforehand. If your company wants to send you, there's going to be one in intermediate Haskell. There's going to be one in Elm. There's going to be one introduction to functional programming using PureScript, I think. And then I might do the advanced functional programming in Scala one, and there might be another one beyond that. So there's going to be lots of stuff at the beginning of the week. On Wednesday, there's going to be at least 2 mini conferences so far. One is PureScript Conf, and that's been going for a couple years now and has really great attendance. It's all sorts of interesting topics will probably be covered there. And another one will be really, really interesting for new functional programmers. You should tell everyone about it, because the people putting this together are assuming no background in functional programming, and they're going to motivate everything. So they're going to be like, okay, here's a null, and here's the exception we get with the null. Is there something we can do to avoid getting these exceptions? Oh, look, here's this option data type, and it's going to be basically a whole day of nothing but that. So if you have friends and you want to get them into functional programming, send them up to Boulder on Wednesday for that mini conf, because I think it's going to be great for people new to functional programming. And then in addition to the PureScript conf, LambdaConf will likely have lots of PureScript content, and of course Haskell, Scala, Elm, Clojure, and others besides. What's that? We had a little bit of that, yes, last year. Hopefully we'll have more this year. It's kind of up to, exactly, give a talk. It's up to the people submitting proposals. We had a little, but it was well regarded. Those sessions tended to be pretty popular. So hopefully we'll have more people submitting this year for F#, Clojure, Erlang, Elixir, and some of the other ones. All right, thanks. Oh, yeah?
So at the beginning of the talk, you said or argued that programming languages or current programming languages aren't designed for co-inductive processes.
Yeah.
How would you design a language from the start to support that well?
I think the generators idea is interesting, because you don't have to deal with the complexity of this infinite stream. In Haskell you sort of get this benefit for free, but in all the other eager programming languages you don't, except when you add this generator construct. So that's an interesting way to do some of it. But honestly, I'm not sure I know the right answer for that, but if you started with the main function and changed the main function, and then like progressively changed everything downstream from that, it's relatively hard for us to write incremental programs that do incremental computation, which is one of the most interesting applications of stream processing. An example of that is a compiler. Like, what you really want your compiler to do is you edit a single character and it does the minimum amount of computation necessary to recompile and do everything like that. And if you write your entire compiler as a co-inductive process that feeds off these patches coming in, you can do that. But oh my God, that's nasty, that's messy, it's just awful. It's just tons and tons of code. And I have to believe that somewhere out there, there's a better way for us to be able to write something that's smaller and more compact and maybe less explicit, and have the compiler do more of the heavy lifting, like in the case of the generators added to JavaScript. All right. Thanks again.